So today I'm gonna give you the tutorial about the semantic programming with cross-layer toolchain for edge intelligences. So what's the motivation behind this work is about how to build a runtime chain via semantic specifications. You can think of the semantic specifications as a configuration. You use a configuration to build the toolchain to run the components, or we call artifacts in the SmartEdge, to run those artifacts on the edge devices. And those edge devices, or we call as the SmartEdge nodes, will be the participants of our SmartEdge swarm intelligence. They need to dynamically load and configure components into the decentralized application logic. So here, the SmartEdge toolchain builder comes here. It will combine all the things. He will get the information from the components, artifacts, and the artifacts will have some specification, what kind of device it is required to deploy or install. And our semantic program is from the user or from other functionality unit to give the specification for what kind of application I want to deploy on which kind of devices. And the SmartEdge toolchain builder will combine all this information and integrate them together to build a running toolchain to finish some applications. Okay, before moving to the details about our toolchain, I would like to give an introduction for semantic program and semantic data. So what is the semantic program? It's actually a structured set of rulers. The rulers will derive from the semantic data and describe how we operate with the semantic data. So in this picture is an example about a semantic program. That's the reason if an object enters field of view of a camera, you can imagine there's a camera on the intersection of the road, and you want to query something from the camera. So here we have two blocks. The first one from the line 3 to 5, you can see actually it defines what kind of results we need and what should it be structured or returned. For example, here, this semantic program asks for one data string published to the topic SP01. And this data string should contain the object that enter the camera 106 field of view. And also it requires the results give the timestamp for the detection. And the second part from the line 6 is define the data source, where this string comes from. For example, we need to subscribe the camera smart node 2 from the data fusion 01 topic. And what kind of information should be included in this data source? For example, it's a detection and results, bounding box, or also it's the detector object is a vehicle or not, and also about the confidence score from the detection result. And based on, as we said, the semantic program is the set of rulers. This is the rulers. Based on these rulers, we can query the required data from the string. So then we have the semantic program. Then we still need to know what is the semantic data, and then we can know why the semantic program can work on that. Let's see, there's an image from the intersection camera. Actually, this image contains a lot of information. The thing behind the semantic program or behind any kind of query is to get information from your data. When humans saw this kind of image, we can actually extract information based on our aspects from our expertise and knowledge. For example, you see there's a building, streets, then human recognize, okay, this should be some urban environment on the intersection, and there are a car and a truck there. And those information also, there are some green boxes from the people who work on object detection may realize, okay, these boxes are generated by the object detector and they are bounding boxes. And also the instance classification and confidence score on the detected results. All this information actually is not directly shown on the image. The image is the data only with pixels. The pixel is only the RGB value, it's a triplet vector. So, but the human can recognize this information from this image based on some prior knowledge. Actually, I want to give you another example about how people actually, or how humans extract information from data. From another view, there's a very classic model is called decision tree. Maybe you know that. When we have the data, every data sample is described by some future vectors. Every future vector is defined by some values. Then the decision tree needed to use to split the samples or data by some criteria, optimized criteria actually. So then they split the data layer by layer, step, and then they get the final results. And how decision tree do that with the data to get the information? They define something is called entropy. They call it information entropy. They will trade the data to calculate the distribution of the data to get the entropy. And for every criteria, they will try if with that criteria to split the data, how much entropy we will reduce. The reduced entropy will be treated as the information gain. So actually every step we gain more information. And in the end, we get enough information from our messy data. Then we get the structured data actually to represent this information. So in this kind, the idea is that semantic data is also a way to extract information from some unstructured data, like this. So for semantic data, we need, in here, we use the RDF to represent the sensory stream, for example. To define the semantic data, you need to first use the ontology and then use the data schema to implement that ontology, as shown in the right picture. So the green parts on the right picture is ontology, and then the white blocks are data schema, define this or implement this ontology. In this way, the sensor data, think about that image. It's just a matrix of values, RGB values. Then based on that kind of messy values data, we structure that with this data schema. Then we get enough information about the frame, for example, is from the traffic camera, and the traffic camera has field of view such like this. And based on this ontology or data schema we have, then we get the raw data from the camera, then we convert the raw data from camera to the structured schema, semantic data like this. From here, I'm not sure if you can see that clearly. It's like, let's think about the information behind this image actually is represented in these semantic declarations. Here is the object detector, is the Euro X8. That means the bounding boxes are generated by this Euro model. And also the timestamp of the result is also represented in here. And also the box one is a car, is defined the class SmartEdge car with the confidence score 0.76. So all this information now is finally structured in a good way with our ontology and the data schema, and then it can be further processed. This is what we do with the semantic program and semantic data. Yeah, so now you can see why we can use the semantic program to carry the information we need from the semantic data. Okay, now then we will talk about the implementations and some work inside this tutorial. So the first part will be the SmartEdge runtime architecture. It's about how to integrate the components and distribute them on the edge devices. And then will be two tools I want to introduce today for the work package. First one is the semantic stem. It's done by my colleague Man, and this is the email address of him. If you have some technical detailed question, you can contact him. And the second tool is the Vision KG, very good tool for training image models. Detection models, for example, is done by my colleague Ji Chen, and this is his email. So let's take a look about the SmartEdge runtime. What is the SmartEdge runtime? So as I said, we use the semantic specification to define the deployment. The runtime train will be built, pack necessary components on the edge devices. This is the architecture of the SmartEdge runtime. We have the application specification on top, and this will be compiled by the SmartEdge compiler to generate the RDF queries or Sparkle query. Then this information will be handled by Orchestrator and the optimizer to generate the more reasonable or more optimal deployment for the different edge devices. Then this information will go to the SmartEdge runtime, then to do the deployment. And of course, they use the knowledge graph to get the necessary information for deployment. So this is the overview of the runtime. Then let's see some logic behind it, how it works. Let's say start from the scenario. We want to start a new task on the Swan devices. We have some main components here. First of all is the message manager. We need a communication between different components or different devices to deploy the thing on the Swan, right? So message manager will do the communication between runtime and the external units. Then we have the orchestrator. Orchestrator will distribute the task into executable primitive. Imagine you have a very huge task, like let's say, detect one red car along the whole road. Then on the whole road, you have maybe 18 cameras with maybe 10 edge devices. Then you need to assign this big task to each small devices to do the different thing maybe. So this thing will be done by the orchestrator. Orchestrator will distribute this to the executable primitive tasks. Then you also have the coordinator. As we said, this is about strong intelligence. You have many different strong members, and the coordinator will handle this information about the strong members. Like it will know, okay, there's a new device is added in the strong intelligence, can be usable for some specific primitive task, or if there are some device left the strong intelligence, then we need to inform this information for the whole system. Then the DKG is about distributed knowledge graph to get the necessary information to execute the primitive or maintain the runtime. As we can see from the right picture, that's the sequence diagram of the logic. We have actor. It can be human or can be another functional component. It will send the task query to start a specific task. This query will send it to message manager. As we said, this is the component for communication. Message manager won't do any logical thing for this query. It will just forward this query to the other component, other units to handle it. For example, here we can forward to DKG, and DKG receive this query and will pass the query to give necessary information for next steps. Again, this information is handled back to the message manager, and the message manager will keep forward that, for example, to orchestrator. Now orchestrator receives this big task. Now the purpose is to distribute that. But how? So first, orchestrator needs to ask a coordinator to get the Swan information. By the way, a coordinator will always manage the Swan members. Then orchestrator will know, okay, which edge devices has what kind of information. For example, if it's a CUDA available, or if there's a camera on that edge devices, such like this. And then based on this information, orchestrator probably will ask DKG again to get more specific field information. And then the orchestrator can distribute the huge task to the multiple primitives. Then these primitives information will send back to message manager in order to forward to task manager. So here there's a new thing, it's called task manager. The task manager is the real thing that will execute the primitives on the edges devices. And so task manager, here I show you there's a two node. Node 1, node 2 means we have, for example, two different strong member or different edge device. So message manager receive the primitives from orchestrator, then they send the corresponding primitives to the different node to run the primitive. So every node has a task manager to receive this information. And then based on this, they will create a primitive. This is done by create a new container inside the edge device. So it will run the primitive isolated. It won't affect the primitives running in the same machine. So once the primitive is created, we'll send the acknowledgement to the task manager. task manager will send back the acknowledgement to the message manager. And for each primitive task, it will do the same thing. And after, for example, here we have 2 primitive, and after every primitive is started, the message manager will tell the acknowledgement from each primitive unite node to the coordinator. Then coordinator knows, okay, in my swarm, which member is running which primitive and what's the running status, and it will collect this information and maintain this information for next round. And after this, finally, we can send the acknowledgement back to our actor or our user. Then user knows, okay, everything works well. Then we are running our primitives. Then the next scenario is about how to stop a running task. Let's say we already detect a red car in the whole road for 5 days. Now we don't want to trigger any more red cars. Now we need to stop it. So it's a very similar logical behind it is the actor needs to send a query to stop it. Message manager handle this query with DKG and forward to Orchestrator. Orchestrator contact with the coordinator. Then Orchestrator will send the stop signs to the message manager and forward to the primitive, to the task manager. And task manager will stop these primitives. As you can see, the sequence diagram here means stopped. The identity is killed. And then we get the acknowledgement, and we send back acknowledgement to the actor, and everything is finished. So this is the logical behind the design of the SmartEdge runtime based on this sequence diagram. Then about how to implement this kind of logical or sequence diagram. Here we use the ROS2 to implement these things. So ROS2, if you attend the first, Wednesday's workshop, my colleague Sumit already gave an introduction about ROS2. Here I would briefly say it again. ROS2 is, the full name is Robot Operation System, but you can imagine it as a middleware. It's just for communication. You can pop up information based on the topic. You can create a service to handle the request and send back the response. So this is all you need to know for SmartEdge runtime about the ROS2. So in this diagram, you can see we use the Docker container to run different components to isolate them. So the left side, which is all the components will run in one Docker container, we call intercommunication Docker container. So this is to isolate the internal communication from the P2P communications. Because we don't want on one edge device, we don't want everybody from the swarm, from other device can see our DKG or see our own task manager or see our own orchestrator. This communication should be stopped. Everything should be handled or be forwarded or by gateway by the message manager. That's the purpose for this. And inside this container, you can see we implement the message manager, orchestrator, DKG, or coordinator, task manager as a ROS node. A ROS node is an individual entity in the ROS2 system. So inside the ROS node, we create a service. So every time you want to do something, for example, you want to ask a task manager to start a new task, primitive task, you just send a request to a task manager service, and it will handle this request to establish one new primitive. So every time the task manager wants to run a new primitive, they will create a new Docker container. They will handle the information and generate a new Docker file, and use the Docker to build the image and the container based on this Docker file, and run the primitive inside a new Docker container. And when we want to stop that, we just delete that Docker container. Then everything is deleted, stopped. Okay, this is the ROS2 implementation about the SmartEdge runtime. So the next step, I will have briefly introduction about the semantic SLAM, the work done by my colleague Man. So what is a semantic SLAM? I think most of you know what is SLAM. SLAM is just simultaneously localization and mapping. It's very important for any mobile robots. You need to know your position when you are moving, and you also need to know where you are when you are moving. For example, in the perspective of the human, when we enter the building, we come to the meeting room. Actually, we are thinking about where we should go or where we already passed by. And we know the road or the path we enter here from the door to this room. So actually, robots also need to do the same thing in order to do the navigation purpose. And the semantic SLAM is to combine the SLAM with semantic understanding, which means it gives the meaning and the context of the entities they observed in the environment. And also it will give the relationships of the objects surrounding to the robot. And what's the first step to do a semantic SLAM? Is to generate the semantic data, of course, and to use this semantic data to build the semantic streams. In the right picture, there are two message model inside the ROS2 system. So why we combine the semantic SLAM with ROS together? Because the ROS itself already has a very good data model, or message model we call. So for example, you can see they define there's a message called occupancy grid. This message is from the class of the navigation messages. And what kind of field inside this message or what the data inside it is already be defined. And of course, you can also create your own message model based on some rulers. And this is the standard messages with the header. Then you can get the frame ID and the timestamp. So the first step with the ROS-based semantic SLAM is to use this kind of existing or widely used message model from ROS itself and convert it to the semantic data. Then we need to, of course, define the ontology and the data schema. This is an example. As you can see, the navigation message occupancy grid, we already saw the definition of it in the last slide. Then we define the ontology and data schema based on these things, and we define the relationships between different messages, and use this kind of ontology and data schema. Again, we can generate semantic data and build semantic streams. So after that, we need to link semantic type of spatial objects. In the right picture, you can see there are two images. This one is for instance segment. We can see different color represents different type of object or different instance actually. This is based on the detection from the bounding box. And then we will assign the semantic meaning of each object. For example, the red bounding box represents this object and the green one is here. Then we also convert this information in our grid map. Is in the right side. This is a BV view, so from top. Then now we can know, okay, what kind of objects is surrounding the robot and what's the meaning of that and what's the relation between the different objects based on the data schema and the semantic object detection. So after that, we can finally make the queries over the semantic SLAM, like we did for the intersection camera. So here is a sample about the Sparkle query for path planning. As we said, this semantic SLAM works for a component when you want to do a bigger or more complicated task on the edge devices. So assume we already running all these things in the behind, and then we want to make the path planning to navigate our robot in an indoor environment from point A to point B. Then we need to know, okay, well, we need to check, which needs to check our map. And we need to know if but I forgot to mention is about the occupancy grid is the voxelization of the environment. They grid the whole environment into the different voxels. Every voxel has the probability about occupied or not So if we need to plan a path, we need to know which or where we can go, or where we are allowed to go. So we need to know each cell or each voxel or each grid is be occupied or not. Be occupied means there's something there, so you cannot hit the other thing. You need to make another choose for your path. That's what the meaning for here. So after this, yeah, we can do the path planning for our robot. And here is the framework or the component inside the semantic SLAM. So we use the LiDAR to get the point cloud, use the camera to get the images, and IMU to get the states of the robot itself. Then we can know the velocity or orientation of our robot together itself. And based on the feature extraction, we can do semantic annotation and then refusing all the data together to do the SLAM, which means we need to know the to mapping to build a map from the perception information. Then of course we have a loop closure to detect if there is a place we arrived before or not, or if there's some overlap between different two timestamps from the environment to build a more consistent map. And here is a small demo video. So actually you can see in the bottom left, that's the detection. And you can see there's oops. For example, it's detect, here is a human. So the semantic annotation will be person, with the confidence score is 0.83. And here is the image, raw image data. And on the right side is building the map in this environment. And this detection is based on the Euro. And is working on a small car in our lab, mounted with LiDAR, camera, IMU. You can see it's exploring the environment.
Is it like a stereo camera? So we have to...
It is a stereo camera, but I here only show the one lens. Okay. So the right side is the occupancy map. The black dots means is occupied, the grid is occupied, so we cannot go there. So if we need to define a path, we need to choose the unoccupied voxels or grids or cells. Then we can get a feasible path for navigation. So this is about the semantic SLAM, and then next step will be the tour of vision KG. So what is a vision KG, or why we need a vision KG, or what it can help us? Imagine the traditional use case when you want to train a model with some public data set. Actually, there are many, many different public data sets. The users or engineer or researchers, they need to pick the data set by themselves carefully. If the data set is wrong, your model definitely is wrong. And then you spend a lot of time on this data pre-processing on the data sets, and then you can train your model. This will be very challenging, or not actually will be time consuming when you want to train a model across different data sets, because different data sets, they have different standards for definition of their data. And now Vision KG come up to help you to solve this problem. In the with Vision KG, you only need to tell or send a query, give me 10 images with box level annotation car. And Vision KG will handle this query, and based on this query, it will extract all the car images from different data sets. And then you can use this easily for training your model. So the whole pipeline looks like in this image. Actually, the user only needs to send something in the neutral language. For example, what I said in here. And a large language model is applied or is deployed here to handle this neutral language to generate the query, for example, a Sparkle query. Then this query goes to the Vision KG and do the rest of things. And this Vision KG already be tested with different learning systems, with, for example, Hugging Face, OpenMMLab, and so on. And then we talk about the Vision KG LM powered endpoint, how this work. So we have the large language model. We have the natural language question. For example, give me pictures, include the car. Then we also have the Vision KG schema and the vocabularies. These schema and the vocabularies are used to train the GPT or LM model for our use case. And then after this train, we finally can generate the correct Sparkle query for the data query to get the required images. So this is the pipeline, this is the features, functions for Vision KG for machine learning operations. Our Vision KG provides a GUI, graphic user interface for Sparkle, as you can see in this picture. For here, these are example queries. For the query the image on which YOLO4 can detect something. Yeah, if I look at that correctly. Then user just need to send these example queries, then they will generate the Sparkle query based on the language model. And this the Sparkle query can use for Vision KG. And then you just to click the query button, then you can get the results for the data. Then you can use this data to images to train your model. And another feature is Vision KG provides some pre-trained model already, and also it provides some pipelines to build your own model, or depends on your customized properties. For example, here you can directly use some import some pre-trained model in here, and some defined pipelines here, and then get the results. And the third feature is Vision KG. With Vision KG, users can also directly use the pre-trained model to infer the data and use the inference results to further optimize the query data to meet your customized usage scenarios. And in summary, Vision KG provides an unified framework that standardizes visual data representation. It has efficient data integration and flexible scalability. And Vision KG also gives a comprehensive integrated knowledge based on the knowledge graph and large language model. And it enhances the data accessibility and reducing the need of technical expertise in KG. Okay, so this is all the information about today's tutorial. Thanks for your attention.